lesson on second derivatives. I tried something a bit different with this lesson because I love those videos that I posted to you on your prep. I think the guy who explains them, he explains very clearly. I thought that this was a topic where some of you would remember very well what was going on with increasing and decreasing functions, and some of you could probably do with a little bit of reminding, and therefore I thought it was worth you sort of deciding yourselves how much groundwork you needed to cover. So I hope that was useful, and I hope that it means that this should be fairly straightforward, this lesson. We will see. So what we're looking at here is the property of a curve being concave or convex. Okay. And then points of inflections, which are kind of the boundary line between the two. Okay, so what does differentiating tell us? We know that we have a stationary point and the second derivative. If it's greater than 0, we've got a minimum. If it's less than 0, we've got a maximum. And if it equals 0, all bets are off, and we need to look at points either side to determine the nature. It could be any one of the three situations listed here: local minimum, local maximum, or point of inflection. Concave and convex, this is what we're talking about. Concave looks like a cave. You don't need to remember that. That's just how I remember it. So that's what the curves look like. And these are the notes that you need to fill in. So concave functions. The function is concave when the gradient is decreasing. And that means that the second differential is negative. So that's the condition for a function being concave. Convex is the opposite. We've got a gradient that's increasing, and it's when the second differential is positive. So notice it's not when the gradient is positive itself, it's when the gradient is increasing. So here, for example, on this curve, we'd have a very, very negative gradient, and then the value for the gradient is getting closer and closer and closer and closer to 0, and then getting more and more and more and more positive. So the number that the gradient is increasing. Okay, so what you need is this definition. The function is concave on an interval if your second differential is less than 0, and it's convex on an interval if your second derivative is greater than 0. So in this graph, you've got a section that's convex and you've got a section that's concave, like that. Okay. So the second derivative sometimes is negative, sometimes is positive. So given that that's the definition, you've got this to do. So what I'd like you to do now is I'd like you to pause and have a go at finding an example for each of these situations. Okay, so what I did is rather than trying to find the function, I looked at the second differential. So for example, if it's always concave, that means your second derivative is less than 0. So for example, if it was -2, so I kind of reverse engineered this a bit, and I drew a picture of a cave. That was important as well. Always convex, I basically did the opposite. I've got a positive second derivative, and it's from this graph. Concave and convex, I had to think what that would mean in terms of picture. It means that we've got a negative second derivative at one point and a positive second derivative at one point. And for example, if you had a linear function for your second derivative, then whatever value of x you had would make that work out. So again, I did it that way. Convex, concave, convex. I drew a wiggle. It's a quartic, and so the second derivative is a quadratic, and that would have a positive value and then negative value and then a positive value. So I was just doing a little bit of working there. So then I just made up a second derivative and I integrated. So whatever you did, I hope that you went for the low-hanging fruit like I did. Okay. So throughout this, because I think you've got enough background from the videos that you watched last lesson, I'm going to ask you to pause and try the questions and then check your work. So can you pause and try this question? So we're asking when this is concave, which means we need the second derivative because that helps us to work out when it's concave. If it's concave, second derivative is less than 0, and therefore we are looking at this function being less than 0, and therefore those values of x. Okay? And yes, make sure you've got this line in your working, that's important, just show that you understand what that condition is. Second application, when is this convex? Could you pause and try the question? Okay, so here we go. You differentiate once, you differentiate twice, and we need a condition, or we're looking at, okay, well this bit's positive. If we add 2 for it, then it's also positive. So the second derivative is greater than or equal to 0. It's convex for all x on the real line. Okay. So here's a little bit of practice. You've got your functions, your second derivatives, and therefore can you please state where they're concave, where they're convex? Can you pause? Can you try it? And then can you check? Okay. So for this one, the second derivative is a square, so it's positive everywhere, so it's convex everywhere. And then you've got these conditions, you've got these conditions, and you've got these conditions. Okay, now point to note. The definition of convex and concave, they include the equal sign in the inequality. We disagree with that definition of concave and convex, but the exam board has had it imposed upon it by the fact that specifications will have to be uniform. So it's a little bit confusing because when x equals 0, for example, the curve is simultaneously concave and convex, and normally we would say it's concave for x is greater than 0 and convex for x is less than 0. So we wrote to the exam board and they said that if you use the inclusive inequality or the exclusive inequality, as in with a little equal sign or not, they would accept both answers. So don't worry about it too much, but it's a point worth mentioning because it does seem a little bit counterintuitive that it's concave and convex at certain points. Okay. Right, points of inflection. So if your second differential is 0, you could have a point of inflection. And basically what a point of inflection is it's when a curve changes from being convex to concave. So the second derivative changes sign, positive to negative. Now the ones you dealt with probably were also points where the gradient was equal to 0, but I hope that you can see that that's not necessarily the case. Like this can be a point of inflection without being a point where the gradient would have a value of 0. I love this animation. I'm going to let you watch it. So there's the tangent, and it's above the original function. Oh, it's below the original function. And oh, it's on the original function. So there we go. I think that's a neat visual demonstration of what's actually going on. So we've got a blue tangent when it's convex, it's green when it's concave, and it's red when it lies, when it's on the inflection points. Anyway, I think that's really neat.